Okay, so restoring force. The classic example of this is a mass on a spring. So if I draw, we have a spring, and we have a mass, and this is a frictionless surface. And if I pull the mass this direction, if I displace it that way, what is the spring going to do to it? If I pull it to the right, what does the spring do? Which direction? Back to the left. And the force from the spring is given by the equation F equals negative kx, where the negative tells you it's the opposite direction. The spring, if I displace it to the right, the spring pulls it back to the left. If I squish it to the left, the force is back to the right. So we call this a restoring force because it's always trying to restore equilibrium. And it's directly proportional to the displacement. Not the displacement squared, not the displacement square root, directly proportional to the displacement. And so we can apply Newton's second law to this situation. You know there are other forces here. There's gravity, there's normal, they cancel out. We've specifically said it's frictionless. So the only force that makes any motion change is the spring force. So if I start from Newton's second law, just like we did yesterday, I get negative kx is equal to ma. And then what do you know about acceleration? How does it relate to displacement?
It's the second derivative.
It's the second derivative. Let's actually write that out. Yesterday we used that acceleration was the derivative of the velocity. But today we don't have a force proportional to velocity. We have a force proportional to displacement. So we need to use that it's the second derivative of the displacement. Okay? So that's what I'm going to plug in here. So negative kx equals m d squared x dt squared. And the way this is usually done, we are going to solve for the differential by dividing both sides by m. Sorry, I don't know why I moved that over so far. Now, yesterday at this point, we rearranged, we separated the two sides, we set up the integration symbols, and it looked like some of your heads were about to explode. Today, it's a whole lot easier. You already know what the motion of a spring looks like. What does a spring do? Like, if I pull it back this way and let go, does it stay there? No, what does it do? It moves this way, it oscillates. It goes back and forth and back and forth and back and forth and back and forth and back and forth. Anybody know a function that describes oscillation? Especially those of you who are either in pre-cal or those of you in calculus took pre-cal last year. What describes oscillation? What function? One of them starts with an S, the other one starts with a C.
Is this sine and cosine?
Sine and cosine.
Oh, yeah.
So,
Even though I'm
this is a valid way to solve a differential equation. It's called guess. We are going to guess a general, and because the College Board uses cosine, we could do cosine or sine here. Those of you who are in pre-cal, you know that graphs of sine and cosine are identical, just shifted by pi over 2 radians. So it used to be, most textbooks, no, half the textbooks in the world choose sine, the other half do cosine. The College Board does cosine, so we're going to do cosine. So the most general equation for the motion, x of t, would be the amplitude of the motion, how far did I pull it back, times the cosine of something times, some constant times time, plus something else. So I'm not looking for a parent function here. The parent function would be just cosine t. But I know that I can make a sine function bigger and smaller. I also know that I can change, are the oscillations fast or slow? And I also know I don't have to start from the origin. I can start any place I want to. So this is the most general cosine function that exists. If it is possible that it solves this equation, But notice there's not a matchup right now. So before we go too much farther, those of you who are in calculus, have you done derivatives of trig functions yet? You have? Okay. So even though we're going to start from cosine. What's the derivative of cosine?
Negative sign.
Very good. Negative sine. And what's the derivative of sine?
Cosine.
Cosine. So the only difference is they're each other's derivatives, but the derivative of cosine is negative sine. It's a sine flipped vertically. So we're going to use that because we need, for our differential equation here, we need the second derivative of the position function. So we need to take the derivative once, because remember, you can't take the second derivative automatically. You have to do the first derivative, and then you do the second derivative. So a is a constant. We leave it in front. I need to do the derivative of cosine, which we just came up with as negative sine. And I'm going to leave some space. And I copy everything that's inside. And then I apply the chain rule. I also need to do the derivative of the inside. Now I'm taking the derivative with respect to time. So this is a constant times time. So the derivative is just, and this is Greek letter omega, by the way. That's not a W. This is omega. So the derivative of omega t is omega. So I have to put that outside. This is equivalent to the starting location. It's a constant after you have a particular motion. So we're done. There's our first derivative. Now we do it again. D squared x dt squared equals, I copy, negative a omega. What's the derivative of sine? Sine is just cosine. So the derivative of sine is just cosine. I copy the omega t plus theta. I again need to take the derivative of the inside. Well, it's the same thing, so I just get omega again. So I end up with an omega squared. And then this is what's cool. Remember, this is the equation we're trying to solve. So now we're actually going to do it. Negative k over m times x. Well, x is this whole function. A, let me slide this up, but not too much. There we go. A times the cosine omega t plus v equals. On the other side, I need the second derivative. Well, that's here. Negative omega squared cosine omega t plus phi. What magic happens? I'll give you a second. Finish writing it down, and then we'll talk about what magic happens. It's not magic, it's math, but you know, it's so beautiful. Let's call it magic. So, what's something that cancels out? The negative signs. What else cancels out? There's not an omega squared on both sides, but there's an a on both sides.
There's an A, there's cosine
And then the whole cosine function.
function.
There's not a lot left. On the left, we have k over m. On the right, we have omega squared. So, to give you a name for this, omega coming from this function, you can see it's something related to time. So those of you who are in pre-cal, are you doing trig function graphs in pre-cal already?
Yes.
Yes, okay. So you know that in pre-cal you always use radians. And so this inside has to be equal to radians. So this is the initial position in radians. If this is time in seconds, this thing must be in radians per second. Omega is in radians per second. That means omega is called angular frequency. Now, we used it in this class last year as angular speed, because angular speed and angular frequency are the same thing, radians per second. We used it in AP1 last year. Not all of you were in AP1. So I can solve for the angular frequency of this. Omega is equal to the square root of k over m. But I don't want angular frequency. I want regular frequency. And here's how I remember the connection between those two. Omega is radians per second. So omega is equal to 2 pi times regular frequency. Okay? And then I actually don't even want frequency. I want period. I want to know how many seconds does it take this thing to oscillate back and forth. What's the relationship between frequency and period?
This is reciprocal.
They're reciprocals. So omega is equal to 2 pi over the period. Or period is equal to 2 pi over omega. And so in this space, I just have to box this answer. My period for this motion is 2 pi, and then I need to divide by this square root thing. When you divide by a fraction, what do you do with it? You multiply by the reciprocal. So I'm going to write times the square root of m over k. And those of you who are in AP Physics 1 should say, wait, I recognize that. That's the time period of a spring equation. Yes, it is. And now you know where it came from. And the thing I've always liked about restoring force as opposed to drag force is that we didn't have to do any integration. We didn't have to integrate this thing twice to get back to x. We guessed the solution, and then we said as long as the period for the motion is equal to 2 pi over times the square root of m over k, then this equation works. This is the correct solution. Okay? So I want to do 2 more things with this equation. Actually, I only want to do 1 more thing with this equation. I'm not going to make you do acceleration also. Let me double check that I am correct. Nope, I am. Okay, so ready to turn the page? So I'm going to copy my position function. The most general possible, x of t is equal to a cosine omega t plus phi. And actually, I don't need to do this. We already did this. I just want to label it differently. We already took the velocity as the derivative of this, right? We already did the velocity. Negative a omega sine omega t plus theta. And then we did the second derivative. And what's the derivative of velocity? Acceleration. So I didn't have to redo the calculus. I've reformatted this left side. But I want to point something out about this. A means the amplitude. What does amplitude mean? Like, use different words to define it.
It's the time it takes.
It's not the time. That's the period. Period is the time for one cycle.
The time it takes to light.
Not time. So one of the ways you can say it is the top to the bottom divided by 2. That's usually what's used in pre-cal. In physics, we usually say distance from equilibrium. So how far did you pull it back to the right if you just let go? So the negative sign is telling you opposite direction. What is a omega going to be equal to? Notice it's in the velocity function and it's out front. So what's the equivalent if this is maximum position? What is this coefficient? No, because now we're in a velocity function. So this would be maximum.
Velocity?
This is maximum velocity. And then what's this? It's in front of the function to find acceleration. So what is this? That's the max acceleration. Okay, and of my plan for today, there were 3 pages. I've already finished the first 2, so I didn't even write as much here. And then just remember, when you're doing this, instead of using the period equation, you want to go back to omega equals the square root of k over m. Okay? unless it's given in the problem. If you're given a cosine function, there's omega right in front of the t. Okay? So, the second example I want to do is if we did mass on a spring, now we're going to do a pendulum. So, we have a pendulum, so it's a long string with a mass in the end. We're only going to do a simple pendulum. So this is the length of the string, mass m. What forces are on this mass?
Gravity.
Gravity downward and tension at that angle. So the tension and the gravity component often opposite the tension cancel each other out. But gravity this way is what's pulling it back down. And you know, the higher you pull it up, the faster it moves after you let go because there's more gravity. So we have, again, a restoring force. So the restoring force is equal to the component of gravity right here. So FG restoring. I don't want to get into X and Y here. Now I'm defining the angle from the vertical. And I drew that, yeah. I want to draw it that way, and then I'm going to draw something else. So that's why it's sine. Do you see it's opposite? Because gravity would be straight down, and this is the opposite side. So that's why it's sine. Now, of course, we know that is mg sine theta. So we're going to go into Newton's second law. Net force equals mass times acceleration. So, and I have displaced this to the right. The force is to the left. So we do have this negative sign. So I'm going to add that in. So we have negative mg sine theta equals m. And what's acceleration?
A omega squared.
No, that's the maximum acceleration for a spring.
It's
In general, back to the beginning of the year.
D squared T over.
It's the derivative of velocity or the second derivative of position. And I want that one. So d squared x over dt squared. Now we can't solve this as written because we don't have a displacement on the left. We have the sine of an angle. So we are going to make an approximation. We are going to say that this distance, x, this is approximately a right triangle. If you do small angles, this is a right triangle where L is the hypotenuse. So for small angles, the sine of the angle is equal to x over L. So I'm going to plug that in. Hey, before I do that, what cancels? M. So negative g, instead of sine theta, I'm going to use x over L equals d squared x dt squared. If I move this over, do you see that this is the exact same equation we just solved for springs? Let me give you a second and I'll put it back on I'll flip back the paper. But we have a negative constant times the displacement is equal to the second derivative of the displacement. So I see a couple of you still writing. This is the difference of doing it live versus when I do it at home, or not at home. If I do it just in an empty classroom, because I'll just, keep going. So then you have to pause the video, but So if I flip back 2 pages, actually just 1 page, there it is. Negative constants times x equals the second derivative of x. And we said this is our function that solves it if omega is equal to the square root of k over m. Omega is the square root of the constant. So for this, the solution would be the same thing. X of t equals a cosine omega t plus phi, but now omega is the square root of g over L, the square root of the constant. And then period, remember, is 2 pi over omega. So it's 2 pi square root of, I'm dividing, so I flip it over, L over G. And those of you who were in my class last year should also recognize that, period of a pendulum. But again, this is where it came from. And one of the things that always bothered people about pendulums is you want the mass to matter, but you can see now why the mass cancels out. Mass does matter, there's more gravitational force, but if you're looking at motion, to get the acceleration, you end up dividing by the mass, and so it cancels out. So you and your baby cousin who are sitting on the swing set, if the swings are the exact same length, you'll have the same period as you swing back and forth. It doesn't matter to different masses. Okay, so that's the end of the video. I'm gonna hit stop. If I can get my mouse over there.